Oh, Rails. For lesson 3.2 on intervals of increase, one of the problems that we sometimes have is that students don't see the need for a tool until they need it. So they won't practice the tool when they have simpler situations. This is where our textbook is a little bit odd because it's an older textbook and it assumes that we haven't done any curve sketching in advanced functions. So you're going to find that a lot of the questions give you polynomial functions whose intervals of increase you could probably predict without using any kind of chart or test value strategy. Using a sketching strategy is kind of putting the cart before the horse now. So what I wanted to do is at least one example where we're sort of working blind, where maybe at this level we're not sure what this function is going to look like. And this is a type of question I want you to prepare for. Imagine the question just asks you to state the intervals of increase for g of x, and I want you to justify algebraically. So we're not going to pull up Desmos and graph this and then say, oh yeah, that makes sense for the intervals of increase. We're going to use the intervals of increase to help us draw the sketch of this curve later. But pay attention to the directions. I'm not going to waste time finding the x-intercepts and the y-intercepts and the domain and the range of this function if I'm just asked to state the intervals of increase for this function. Okay, so let's try our definition and our approach. To figure out when a function is increasing or decreasing, or neither, I'm looking at the signs of the derivative because that will tell me the signs of the rates of change or the signs of the slopes of the tangents. Whether they are positive or negative tells me whether the function is increasing or decreasing. Okay, so I'm going to need the derivative. If you want to take a step to just sort of tidy up the function or prepare it for differentiation, seeing this as a difference of squares, I don't think is going to give us any advantage. Writing a difference as a product is going to complicate things. So I'm just going to write the radical as a rational exponent here. Then I can jump into the product rule. G prime of x is going to be the derivative of the first multiplied by the second. Let's see, plus the first multiplied by the derivative of the power with respect to the base. Make sure I subtract 1 from my exponent, multiplied by the derivative of the base with respect to x. Okay. And I think I'm going to tidy up before I start factoring. Let's see, I don't really need this 1 here, so let me just write this as 4 minus x squared to the exponent 1/2. Let's do negative 2 times 1/2 is going to be negative 1. X times x is x squared. And then I'll have 4 minus x squared to the exponent negative 1/2. This is a case where the derivative looks a little bit more complicated than the original function. Okay, so I don't think sketching the derivative is a good approach to figure out when the original function is increasing and decreasing. Because if I could sketch this, I could probably sketch this, and then why am I using a derivative in the first place? Okay, let's take an algebraic approach instead and get this into factored form, because factored form is where we see our factors, and factors is where we see sign change. Let's remove the greatest common factor. Let's go with the power to the smallest exponent. I'm going to remove a factor of 4 minus x squared to the exponent negative 1/2. Big square bracket to draw my reader's eye. Something to the exponent 1/2 divided by something to the exponent negative is the same thing to the exponent negative 1/2. I'll keep my base, subtract my exponents. 1/2 minus negative 1/2 is 1/2 plus 1/2, which is 2/2, which is 1. So I am left with 4 minus x squared to the exponent 1. Take a factor of 4 minus x squared to the exponent negative 1/2 out of this, and I'll be left with a minus x squared. So that tidies up an awful lot. Now let's tidy this up. I think for sign analysis, I kind of prefer having radicals and natural exponents. So I'm going to leave this up in the numerator. I'm going to have a factor of 4 minus 2x squared in the numerator, and a factor of the square root of 4 minus x squared in the denominator. And then as far as our argument for sign change goes, you know what? Maybe we want to write this in a fully factored form first. Let's remove a factor of, we might not. I don't know. We'll see. Yeah, I don't want to have to write out the denominator every time, but I think it's the right thing to do. Let's remove a factor of 2, leaving with 2 minus x squared. Square root of 4 minus x squared. And then here's one of our chances to use this forced factorization. It's going to help us a lot with analyzing sign change. Let's go 2 times. I'm going to factor this as a difference of squares. 2 is the square of root 2. You can check this with distribution if you don't trust the instructor. I'm not bothering to factor the denominator. I'll talk about why in a sec. It's the fact that it's underneath the square root symbol, an even root symbol. Yeah, root 2 times root 2 is 2, plus x root 2 minus x root 2 would be 0 x's, or 0 root 2, so however you count it, minus x squared. Looks good. So now I am going to justify my chart here when I look at this and I say that this thing with a square root of experiences no sign change. Okay. It may be neutral when x is equal to 2, but it does not experience a sign change. So all I need to be careful about is the fact that I don't think my function exists when x is equal to 2. I think I will have to then include this in my factor interval chart and include its root of plus or minus 2. Maybe I should have it in a factored form. I think I'm going to go back and do that. Let's go 2 minus x times 2 plus x. Still no sign change in this expression. No sign change. Okay. I'm wondering if there's a restriction. Yeah, there's a restriction on the domain of this function that I haven't thought about that makes me not worry too much here about what happens at 2 and negative 2. I think we'll see it to be the case. Let's chat about the domain here that I need the radicand to be positive. So 4 minus x squared needs to be positive. That means that, let's go back to my factored form here, 2 minus x times 2 plus x needs to be, positive or neutral. Call that, I don't know, like you could call it R for your radicand function. Draw a sketch of such a function. And you'll see that that's going to occur from negative 2 to 2. So the domain of this function is restricted. It only exists between negative 2 to 2. So I'm not going to be doing a factor interval chart from negative infinity all the way to positive infinity here either. But it's key for me to understand that even though I don't see a sign change at 2 or negative 2, I don't think that the sign of the derivative is going to exist. The derivative is not going to exist at those instances. Okay, let's see what our factor interval chart ends up looking like. Let's do x as an element of, I've got roots at 2, and square root of 2 is like smaller than 2. So I'll go, let's say, at negative 2, from negative 2 up to negative root 2. I don't really need to include at negative root 2, but I think I will just for fun. Between negative root 2 and, I don't think anything sort of special happens at 0. I've got an x-intercept of 0, but it's not a root of my derivative. So I think I can safely go all the way up to root 2, consider what happens at root 2, consider what happens between root 2 and 2, consider what happens at 2. And there is the domain of my function. I guess that's kind of the start of my chart. Factors that could change sign. Let's look at root 2 minus x, 2 plus x, root 2, sorry, plus x. See, this is This is sort of the issue here, is that I know my denominator isn't going to change sign because of this square root of. So maybe I can just consider the sine of the square root of 2 4 minus x squared down here, and just mention that that expression is going to be neutral at -2 and +2. And that means that my first derivative, g prime of x, does not exist there or there. Okay. For the others, might have wanted to maybe switch these factors around. This is a linear function that has a root at √2. And it's a decreasing function. So it is going to be positive before its root, neutral at its root, and negative after its root. This is an increasing function. It has an x-intercept of -√2. It is negative before its root, neutral at its root, and positive ever after. This expression is when you're taking the square root of anything that isn't neutral, of course, it's going to be positive. So you can speed up that analysis a little bit without looking at the sign of all of these factors in here. Okay. If you're thinking, well, what about like when this is negative or this is positive, these change sign across -2 and across +2, and you're not crossing those. So try it out if you like. So here we go. This is going to be a negative sign. That'll be neutral. That'll be positive. That'll be neutral. That'll be negative. So without knowing what this curve looks like, I now know when the curve is decreasing, turning, increasing, and also critical, I believe caused by vertical tangents. It's going to help me out a lot when I sketch this function later, when I throw everything else all together. But I don't need to spend my time worrying about the sketch of this function to answer the question. I was asked for the intervals of increase. I will say, I believe it's justified here, g increases over, there it is, x is an element of, when asked for the interval of increase, please use interval notation and identify it as an interval by saying x is an element of, so your reader doesn't think that it's an ordered pair.